there is a theorem regarding this particular function. That is, we have x to the power of n minus a to the power of n divided by x minus a. For example, it could have been something like this. X to the power of 15 minus 4 to the power of 15 divided by x minus 15. Sorry, in this case 4. So here a is, as you can compare, it is 4 and n is 15, right? We need to make a note of that. Now, what the theorem tells is, if I apply limit such that the x value tends towards 4, when we actually apply this, what happens? 4 minus 4, this becomes 0. But there's a derivation which I'll be doing it now. So the result would be, in place of infinity, we have a definite answer, and that answer is 15 times of, in this case, a is 4 to the power of 15 minus 1. So that would be your result rather than it being an infinity, right? So if I just apply directly, so a small note, if we apply 4 in place of x, so if this being f of x, so that is f of 4, it would be 0 by 0, which is infinity. So at that point, right, if this being f of x itself, at that point the function is not defined. We have seen such an example, right? One of the example is, I think over here, no, the previous one, not that, this one. So at around the point it is defined, but here it jumps off. So this is nothing but x square minus 4 divided by x minus 2. It's same as this actually. So it is x square minus 2 square divided by x minus 2. Around the value of 2, we have an output. Agree? Around the value of 2, we have an output. If I zoom in, you guys can see that. This is 2. Around the value of 2, there are values. And that value will turn out to be something like this. Okay guys, the expression in the above theorem for the limit is true even if n is any rational number and a is any positive number. Okay, the proof being this actually. So for this, you guys need to know a particular formula, that is x to the power of n minus a to the power of n. Similar to your a plus b whole to the power of n from the binomial theorem, we have this formula. So it's similar. You can see the pattern. It's kind of similar. So on and so forth till a to the power of n minus 1. So to the given expression, I'm taking x to the power of n minus a to the power of n divided by x minus a. If I apply this particular thing, let's see what happens. So this entire expression, x minus a times of x to the power of n minus 1 plus dot 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 a to the power of n minus 1. This entire expression divided with x minus a. So here x minus a gets cancelled and we have this expression. So the solution would look like limit x tends to a, x to the power of n minus 1 plus a to the power of n minus 1. So how many terms are there? There are n terms in total. Why is that this is needed? I'll explain. N terms. See, we're starting off with n minus 1 till x being equated to 0. X to the power of 0. So here we have it to be equal to x to the power of 0. So from this n minus 1 to 0, there are n terms. Does it make sense? So n minus 1, like say take 5, 5, 6, or go back 5, 4, 3, 2, 1, 0. From 0 to 5, including 0 and 5, how many numbers are there? Count it. 5, 4, 3, 2, 1, 0. I hope you guys are doing that. There are 6 numbers. Similarly, n minus 1 to 0, there are n numbers. So I have not taught you guys this, but you can apply the limits now. That is, we can do the following. I can, in place of x, I can apply a to the power of n minus 1 plus a to the power of n minus 2 into a, right? Applying to this formula, plus a to the power of n minus 3 into a square. Okay, so this is square, by the way, my bad. Plus the last term is a to the power of n minus 1. So there are basically a to the power of n minus 1 plus this will result in the same expression adding how many times? N times, is it not? So there are n numbers, n such things, so n times of a to the power of n minus 1. And that is our answer. And it's important for us to remember this formula. It is useful in quite a few places.